So in this video, we're going to start to talk about thermal physics, and you'll notice that a lot of this will be a review of what you've learned in a basic chemistry class, but we'll go a little bit deeper into some concepts and quantify things a little bit more than you did before. And hopefully you'll understand it a little bit better when you have the understanding of both the subjects together. So the idea of atomic theory is that all matter is made up of atoms, and that atoms are in constant motion. And just to kind of oversimplify it, we'll say that all substances exist in three different states, one of three different states of matter: gases, liquids, or solids. And a gas is something that has no definite shape or volume. It will fill whatever container it's in. The particles are very spread out, and they have the highest amount of kinetic energy. So this is where you learned about kinetic molecular theory in chemistry, and we'll talk in a second about how that relates to temperature scales. So liquids then, they have a definite volume but no definite shape, so they can fit the container they're in, they flow, they have less kinetic energy, there's intermolecular forces, they're sort of attracted to one another. And remember that they're incompressible, so we talked about hydraulic systems and the fact that you can exert a force on a liquid and it won't compress the liquid, it will transmit that force. And then solids have the least amount of kinetic energy. They have a solid structure, definite shape, definite volume, and the particles are vibrating in place. So just to sort of get an image of that, you can see that this kind of shows you the particles that make up a solid. So it has a definite shape and a definite volume, but even though a solid appears not to be moving, the particles of that solid are vibrating in place. And then if I were to add heat, or pressure, which we'll get into in the third topic of this unit, I am going to increase the energy that these particles have, and eventually they will start to flow past one another and become a liquid, or even expand further and become a gas. So in chemistry, we learn about kinetic molecular theory and how you kind of memorize the idea that kinetic energy relates to temperature. But now that you've taken a physics class and you understand what kinetic energy really is, and if you notice like all these elastic collisions that are going on in here, the kinetic energy relates to the temperature of the substance. So let's talk about that a little bit more in detail. So, if I can get my PowerPoint to cooperate with me here. All right, so the idea of kinetic theory says that the temperature of a substance directly relates to the measure of the average kinetic energy of the molecules of that substance. So this equation, so you really don't look at this in chemistry, but now we can quantify a little bit further, that kinetic energy molecular, so that's average kinetic energy, is equal to 3/2 times, so it's not directly proportional, times K times T. So K is really a constant, Boltzmann's constant. It's just a number, it's a value. If you were ever asked to calculate something using this equation, you'd be told what Boltzmann constant is. And I'm pretty sure it's on your tables of information if you ever need it that you'll have on your test. And the T here is then temperature. And if you notice, Boltzmann constant is joules per Kelvin. So the temperature scale in which this relationship proves true is the Kelvin temperature scale, which is called the absolute temperature scale. And we say that it's proportional to the kinetic energy of the molecules. So the concept or the theory of absolute zero is the theory that when substances or when particles in a substance have zero kinetic energy and are not moving at all, that's when we have something that's the coldest it can possibly be, and we call that 0 Kelvin or absolute zero. Now, there are other temperature scales that we use, and so there are some conversions here. I wouldn't really worry about the Fahrenheit conversion at all. You most likely will never encounter one on a test or anything like that because we don't really use Fahrenheit in science. But down here you can look and see that the conversion for Kelvin to Celsius, and this might be used more frequently. So if you take the temperature in Celsius and you just add 273.15 to be exact, you get the temperature in Kelvin. Notice that the Fahrenheit and Celsius temperature scale has this degree symbol because it's a degree of temperature, whereas Kelvin does not because it is an absolute temperature. All right, the last thing I'm going to talk about in this idea is the internal energy of a substance, right? So remember that internal energy, potential energy, we use this variable U. So again, this is sort of the idea of potential energy, and it's the energy that's contained because there's this kinetic energy inside the gas, or inside the substance, and it's really a potential for that energy that is contained within the matter to then go and move somewhere else. And so that's why, even though it's kinetic energy of those molecules in there, we think of it as the internal energy or the potential energy that the matter has to do work on something else. And this, there's two different equations for this. One relates it to Boltzmann's constant, and the other relates it to moles and a gas constant. We'll look at the gas constant again. You should have heard about it in a chemistry class, and moles in a chemistry class. If you haven't yet, it's not too much to be concerned with. You won't be really far behind. But if we can just look at this and understand sort of the mathematical relationship, that the internal energy of the substance U is equal to 3/2 nRT. So nRT is, N is the number of moles, R is the gas constant, and T again temperature, and we always want to have things in Kelvin. So that would allow us to quantify the internal energy based on the temperature of the substance and how much of the substance you have. Now, if you have taken chem, you will notice this nRT. That should make you think of the ideal gas law, and we'll come back and look how internal energy and ideal gas law relate to one another, and the pressure and the volume and whatnot. Now, if we wanted to relate the internal energy to Boltzmann constant, it's very similar. You can see N is the number of molecules, K is your Boltzmann constant, and T is your temperature. All right, so we most likely won't be actually calculating something, but we can compare temperature to an internal energy in sort of a qualitative in a qualitative way. So in the next videos then I'll start to go into the idea of gas laws and changes of pressure, temperature, and volume, and then we'll get back into talking about this energy when we talk about the conservation of thermal energy and thermodynamics.